Welcome back, AP. We have 4.4. We're going to learn the last two reactions in this section. Single replacement reaction is also known as oxidation reduction. Before I get to oxidation reduction, because that is number 9, let's first learn what single replacement is. There's a general pattern to it. So you got to remember, double replacement was when you had the replacement of two ions. So the positive and negative, that positive was replacing letter C and was bonding with A and D. And then C was replacing A and bonds with B. But remember, cations always have to go first. Well, the same principle for single replacement, except you're just replacing one. So let's assume A is a metal. So if A is a metal, and I'm just going to put an M, you got to remember cation and anion, this metal is trying to replace that metal, okay? Because remember, it's positive. So that metal is trying to replace that metal, and if it is more reactive, then they'll swap places. So now B will be the single element by itself, and A will form a compound, an ionic compound, with whoever X is. Okay? Let's assume A was a non-metal, though. Okay? So this non-metal, positive and negative, this non-metal is looking at that non-metal. And same thing. If it's more reactive, that A and X swapping places, the B is still the metal. A is the non-metal, and now the X is all by itself. But notice I said if more reactive. So the question is, how do you know if an element is more reactive to replace it? So we have to use something. So to determine if an element will replace another element, we have to use something called the activity series. An activity series is a chart, and you only use this for single replacement. Notice we have never mentioned this chart about any reaction so far. So activity series, we need it for single replacement. It's a list, and it's a list of metals that go in order of decreasing oxidation. Now I know oxidation doesn't mean anything to you yet, but the metals at top of the activity series are what we like to call the most reactive metals. So the ones on top, so you're going to see a list in just a second. The metals on top are the more reactive, and the metals on the bottom are less reactive. So these elements that are on top, they can replace anybody below them. So metal in the activity series can only be oxidized, aka replaced, by a metal below it. It doesn't work the other way. So if I try to have a metal that's down here, try to replace somebody up here, not going to happen. So you have to have a metal that's more reactive than who it's trying to replace. So, a sample example of this. Active metals on top of the list. Well, let's look at this list. So the activity series is right here. And yes, you will get this activity series. Elements on top, these are very reactive. And the reason why is because look at what elements we're talking about. Group 1. Group 1, Group 2, 2, 1, 2, 3. Most of the periodic table on the left side, these are very reactive metals. Look at the bottom of the list, who's not too reactive? Okay, so starting about right here on, you get transition metals. Okay, hydrogen. What the heck is this guy doing in here if this is called the metal list? Well, I'll get back to him. But then you even got even more transition metals. Very unreactive. So as you go down the list, it gets less and less reactive. Now, this has to make sense to you. Why would copper, silver, mercury, platinum, gold be very unreactive? We don't want them to be reactive. I mean, we wear gold and silver on our bodies and jewelry. We have them in our pockets as coins. We don't want them blowing up on us, on our body, in our pockets. So that's why it makes sense that they're very unreactive. We're not carrying around lithium and potassium and calcium in our pockets or our body. Not that I know of. Okay, but if you are, we gotta have a talk. But why the heck is hydrogen here? Well, you gotta remember, what do we know about metals back from honors in CP? Metals lose electrons and become cations. Well, doesn't hydrogen do the same thing? Hydrogen only has one electron. And so when he loses that one electron, he becomes H positive. Hydrogen in a balanced equation always acts like a metal because it loses that one electron. So that's the reason why hydrogen's here. Notice also you don't see any nonmetals. This is only the activity series for the metals. So how does this play out? Well, let's look at this copper one. Metals on top replace less active metals on the bottom. So this copper, you only focus on the element. And we have to ask ourselves the question, is he more reactive than silver? And the reason why we're looking at silver is because silver is a metal. So remember, metals can only replace metals. Make sure you write that down. Metals replace metals. So if I look for copper, well, copper's down here at the bottom, and silver is sitting right below him. Well, copper, being more reactive, he can replace silver because silver is below him on the activity series. So they'll basically swap places. So what was the charges? Well, silver was +1. Nitrate, polyatomic, because it's going to dissociate right there, -1. So then you get to this copper. Well, how do you know which copper's charged? Well, you look at the activity series. And the copper's charge that they're using +2. They're not using the other copper +1. So that's how you know what charge to use for that copper. So +2, -1, crisscross, so forth, so forth. Now silver is the element all by itself. Quick little balancing with coefficients, and that's pretty much it. So when you get to the net ionic, you're going to notice you actually have a spectator. Your spectator is going to be the nitrate. Okay, I just didn't show that middle step. Okay, but your spectator will be the nitrate. So I'll have copper solid, 2 Ag plus, my copper +2, and my 2 Ag. And that's pretty much it. Be very careful when it has a reaction with water, okay? Because you have to think of water in that ghetto version of HOH, okay? That nitrogen is trying to replace the hydrogen. Well, you can't think of water, H2O, as it dissociates this way. Water doesn't dissociate into H into O. Water actually dissociates into H and hydroxide. That's how it dissociates. So unfortunately, right above it, you're going to kind of have to write water in that ghetto version because sodium sits right there. And notice where hydrogen is? Oh, he's several elements below him. It's definitely going to happen. So sodium will replace the hydrogen, and I'm going to get now sodium hydroxide. And then I will have the hydrogen sitting all by itself. And I apologize, this hydrogen should not be there. I'll fix that in the notes. So sodium will replace the hydrogen, and then now you'll have sodium hydroxide aqueous. Now, why do I dissociate this sodium hydroxide? Because he's a strong base. Okay, as we saw in video 4.3, we learned that he's a strong base. And then H2, why H2? Because he's a diatomic. So I can't just put hydrogen all by itself. And we know hydrogen is naturally a gas. Okay, and then go back and quickly balance your equation. Which I believe it looks like we're going to need a, let's see, we have 2 hydrogens here, we have 3, so it looks like I'm probably going to need a 1/2 sitting right there, okay? So disregard that H right there, that was not supposed to be there. Single replacement is when an element's trying to replace a metal in a compound, okay? There is an activity series for nonmetals. It's a very, very short activity series, because it's only the halogens. Well, that makes the life simple if we only have an activity series for the halogens. So this right here, group 17 on the periodic table. Notice fluorine is the most reactive. Iodine is the least. Okay? Well, here's a cool trick. look at group 17 and the order that they're listed. Fluorine's on top, chlorine, bromine, and iodine. That's literally the list. Nothing to memorize, okay? So fluorine is the most reactive. And students get this very confused. Do not confuse it with strong acids and weak acids. The reason why is because strong acids, HCl, HBr, and HI. But fluorine is the only one in this group that's actually a weak acid. So be very careful when you're trying to think about reactivity versus strong versus weak acids. Okay, these are completely two different topics. Okay, so on the activity series, fluorine is the most reactive. Okay, so active nonmetals replace less active nonmetals. So as long as the element on top is higher up on the chart than the element on the bottom, they'll replace. And the reason why fluorine is the most reactive is because he has a very high electronegativity number. He's the most electronegativity. So remember, electronegativity is that ability to gain electrons. He wants to gain electrons the most in that whole group. And we'll get more into electronegativity when we get to chapter 9 and 11. Okay, so trust me, lots of that topic coming. Let's do a little practice with this. So I'm going to move my notes like this so I can see the activity series over here. I have iron shavings, so that means iron as a solid, and it's added to a solution of Pb plus 2, and then chloride, Cl minus. That word solution just told me aqueous, so I don't even need my activity or solubility rules because it just told me everything that I need. But I do need to balance my charges. So now this is where it comes. Iron is looking at that metal right there. So iron is looking to replace lead. So the question is iron more reactive than lead? So we got to go to our chart. I see iron right there, and I see lead a couple elements below, and yes, this will occur. So iron will swap places, but which iron is on the chart? Iron plus 2. And then chlorine, Cl2, because iron plus 2, Cl minus, I got to do a little crisscross. And then right here, I'm going to have Pb, solid, sitting all by itself. Now, according to solubility rules, you'll have to look on the rules, but it will be aqueous. I don't have them in front of me, but it is aqueous. So now the question is breaking whatever you can break. So remember with ionic, you can only break aqueous, ionic, strong acids, and strong bases. Well, I don't have any acids or bases. I do have 2 aqueous. And those aqueous are ionic, okay? So I can break those up. So Fe, solid, I automatically know these 2 I can't touch. And then I get Pb plus 2, chlorine minus, remember bring that 2 in the front, and then Fe plus 2, and then chlorine minus, same thing, bring the 2 in front. And remember, we can't touch those solids. I do have a spectator. My chlorine is my spectator. I have 2 on each. And now the net ionic. So with my net ionic, I'm going to not only make sure I have the right amount of elements on each side, I'm going to make sure I have my states of matters, and I'm going to make sure my charges are balanced. Over here, and I'm just going to do it in a different color. Never do this in your final answers. I'm going to do it up here. My iron has no charge. My Pb is plus 2. It's got to equal plus 2 on the other side. So my iron's plus 2 and my Pb is 0. Okay? What types of reactions? Well, we already know it's single replacement because that's the topic we're talking about. Is it any other? Well, I see a precipitate. Okay? So there's a video coming right at the end of this where we are going to do a summary of all 9 types. But we got to get through all 9 types. All right. Next one is, and I'm going to keep my activity series right here so I can go back and forth. piece of sodium. And actually, I'm going to pick a different element. So I'm going to edit my notes. The reason why, because we just did an example of sodium above. Let's do potassium. We'll go potassium. Potassium's added to a drop of water. So sodium, let's get rid of the sodium now. So potassium is a solid naturally. Water, H2O. Water's a liquid. So now, according to our chart, is potassium more reactive? But who is he looking at to react? So you got to remember, you got to think of water in that ghetto type of way. That potassium's looking to replace that hydrogen because it's going to dissociate between the H and that OH. So is potassium more reactive than hydrogen? Oh, you bet. Group 1, right there, he's the second one. He's going to definitely swap places. Well, potassium and hydroxide, we already know hydroxide's -1, potassium's +1. That looks good. Potassium, group 1, always aqueous. And then I'm going to get that lonely hydrogen, but he can't be too lonely because he's diatomic and naturally a gas. Real quick balancing, I'm going to get my 1/2 on that O2 gas. So now what can I dissociate? Well, I can't touch the solid, can't touch the liquid, and I can't touch that gas. So the only thing I can dissociate is that KOH, which means I don't have any spectators. So my final answer, and I'm not even going to bother with this step, I'm going to go K, and then my water. I'm going to dissociate my K and my OH. And then my 1/2. So I still have single replacement, but I also have gas evolution, okay, because I did form a gas. A piece of zinc, mossy zinc, so that's a solid, and is added to hydrochloric. Well, hydrochloric is HCl. So now the question is zinc more reactive than hydrogen? Well, let's go look at our list. And zinc is more reactive. So that zinc will replace the hydrogen. Now, which zinc are they talking about? Well, zinc only has one charge. Zinc is always +2. So Zn +2, chlorine -1, do a little crisscross. And zinc chloride, according to solubility rules, will be aqueous. And then I get my diatomic hydrogen. Okay? Zinc, HCl. HCl is one of the 7 strong acids, so I can break him apart. That aqueous is ionic. I can break him. And then that gas, I can't touch. So these two right here definitely can't touch. But before we start dissociating, let's make sure we're balanced. We do have 2 hydrogen and chlorine, so it means we need a 2 there. So net ionic, I got my zinc. My 2 HCl, I'm going to dissociate my 2 H's and my 2 Cl's. And then for my zinc chloride, zinc +2. My chlorine, bring that 2 in front. And then I can't touch that gas. So do I have a spectator? Well, I got chlorine again as a spectator. And now everything's left over. So zinc, my 2 hydrogen aqueous, my zinc ion, and my H2 gas. So not only checking that I have 2 hydrogens for every 1 zinc, but check the charges out. Right here is zinc, I'll put it down here, has no charge. This hydrogen's not +1 because I got 2 of them. He's really +2. And it has to equal that zinc, and then that hydrogen has nothing. So when you're checking your work, ladies and gentlemen, please make sure you don't do it in the box, do it outside. It is still single replacement, and I did have some gas evolution. Okay? So, chlorine gas. Well, chlorine's a nonmetal. And it's bubbled through chromium 2 iodide. Well, chromium iodide 2. and it did say solution. Well, because chlorine is a nonmetal, I have to look to replace the nonmetal in iodine. So the question is chlorine more reactive than iodine? Well, we got to go to the activity series chart for the halogens. And notice chlorine is sitting right there on top of iodine, so they'll swap places. So Cl2 gas and chromium iodide, they will swap places. So now you're going to get, it's basically like a merry-go-round of swapping places. I'm going to get that Cr and chlorine. Cr is +2, chlorine -1. And that will be aqueous with solubility rules. And then now iodine by itself, but he's diatomic. And naturally, iodine is a solid. So with balancing, looks like everybody's balanced. So I can't touch that gas. I can't touch that solid, but I can touch these two ionics because they're aqueous and ionic. So I'm going to get my Cl2 gas, my chromium +2, my iodine, bring that 2 in front, my chromium +2, so it looks like chromium is going to be my spectator, and then my I2 solid. So bye-bye chromium, and now what's left? Same thing here when you're checking your charges. Iodine looks like it's -1, but remember 2 times -1, it's really 2 here, and that's a 0. My 2 chlorine, same thing, 2 times -1 is 2, and then my diatomic iodine. So automatically single replacement. I'm going to get some precipitate. And then my spectator was the chromium. So you're probably asking yourself the question, well, every example that we've done, it replaces. What happens if it doesn't replace? Well, let's take number 3. Let's take number 3, and actually, I just lied. Let's take number 1. Let me go back to number 1 since I have space right here. So in number 1, let's switch it. Let's say this time lead shavings are added to a solution, and you can abbreviate the word solution, SOL', to a solution of iron to chloride. Okay, so if I had PB solid and it's added to a solution of Fe2Cl, balance my charges. So lead, being a metal, is looking to replace that iron. So on the activity series, let me erase all my circles over here. Lead is down here, and he's looking to replace somebody higher on the activity series. And lead is not more reactive than iron. Because he's not more reactive, he can't swap places. There's no swapperoo. So if he's not more reactive, then no reaction. So only doubles and single replacements, you can only think the words no reaction only with those two types. So that would be your molecular equation. What would be your net ionic? Well, I don't want you to think it's that same answer, because this is ionic. This is aqueous. I can still dissociate that. So my final answer would be PB solid, Fe+2, my chlorine, but now I have 2 of them, and then no reaction. So what type? Well, it was still single replacement, and why? Because I had to use the activities series to figure it out. It's still single replacement. No reaction is what happened. But what about spectators? Well, there's none, because there was no reaction. Okay, so nothing occurred. I just want you to see what that would look like if you actually had somebody less reactive. Okay, I'm going to zoom back out so we can get to the last type of reaction. Oxidation numbers. Well, in order for me to teach you the very last one, which is called redox, I got to teach you what the heck is oxidation numbers. Oxidation number is like a tracking of electrons. It's a system that we use to figure out what the electrons are doing in a chemical reaction. We have to figure out the oxidation numbers for every element. So this is a very important skill that you learn now and master it now, because you're going to need it in chapter 20 big time when we get to something called electrochemistry. My favorite topic. So there's a lot of rules, but as you go through the examples, you'll see how the rules, they're not too bad. It just seems like a lot of them. Elemental form means it's pure form. Okay? Every atom that's in its elemental form has an oxidation number of 0. Okay? I say diatomic hydrogen because hydrogen exists naturally as H2, has an oxidation number of 0. Pure elements, all 0. Other diatomics, still 0. So elemental form, the oxidation number is 0. So basically the element sitting by itself is 0. What if you have what's called monoatomic? Well, the word mono means one. Atomic, element. Ion means a charge. That means the oxidation number is the charge that you see on paper. I see nitrogen -3, so that means because I physically see that -3, that means the oxidation number is -3. I see O -2, which means -2, so forth, so forth. Aluminum +3, +3. So there is a trick. Every element in group 1 will always have an oxidation number of +1. And everybody in group 2 will always have an oxidation number of +2. All other metals you're going to have to figure out. But I will give you another hint. Aluminum will always be +3. Okay. Boron, even though he's not a metal, I'll put boron down here. Boron, which is also in group 13, will also be +3. Nonmetals are usually negative. The problem is what happens when a nonmetal is bonded to another nonmetal. That's when it gets a little tricky. Okay, so metals will have positive oxidation numbers. Nonmetals, can't say the word always, usually will have negative. Now we got some rules about particular elements. Fluorine, always -1. And let me show you what I mean by that. Fluorine is -1. That means this hydrogen has to be +1. And the rule that's coming is that neutral compounds, the oxidation numbers have to equal 0. Just like when you're doing your crisscross balancing. Same thing. Fluorine's -1, so sodium has to be +1. This fluorine is -1, but you have 4 of them. So it has a total of -4. So that must mean carbon is +4. But what's the answer? When you're doing oxidation numbers, it's for one of the elements, not all the elements. This is just to get me to equal 0. But what are my answers? It's the +4 and the -1. Fluorine is -1. 1 times 3. That must mean nitrogen has to be +3. And F is -1. 1 times 2. That must mean oxygen's +2. Okay, because 2 times -1 is -2. And that's how it equals 0. So remember when I said nonmetals are usually negative? And look what happened. Carbon and oxygen actually had a positive oxidation number. So you have to need to write this down also. Oxidation numbers are not the same thing as charges on the periodic table. They are totally different. Oxidation numbers, it's a tracking of the electrons. Okay? Charges just tell me how many they lost or gained of electrons. Oxidation numbers tell me who actually lost the electrons or who gained the electrons, but it's a tracking system to keep track of the electrons. The other halogens. Can't say the word always, but I could say the word usually. They're usually -1, unless if chlorine, bromine, or iodine are bonded to oxygen or fluorine, that means then they will be positive instead. Okay, so you got to be careful on who they're bonded to. So chlorine, bromine, iodine, for these right here, okay, they're all -1. I don't see oxygen or fluorine. So remember, I still got to get it to be 0. So hydrogen has to be +1. That sodium has to be +1. Now iodine, 2 times -1 is -2. So that must mean magnesium's +2. But now what happens if you actually see oxygen? Well, chlorine, don't know, okay? But I do know, because there's a rule right here, hydrogen is normally 1 unless bonded to metals. Well, I don't see a metal here. So that hydrogen's 1. And the rule coming about oxygen is normally -2. Okay, not bad. So that means chlorine has to be what to get me to 0? Well, that must mean chlorine has to be +1. So when in doubt, if you have oxygen or fluorine with one of those halogens, you got to figure out the other elements first, then get to the chlorine. Sodium is in group 1, G1, so +1. I don't know bromine because I see oxygen, but oxygen, -2 times 3, -6. So now 1 plus something minus 6 has to get me to 0. Well, that must mean the bromine has to be +5. Okay. Potassium's group 1, +1. I don't know iodine, but oxygen, -2 times 4, -8. I need this to be 0. So 1 plus something minus 8, that must mean iodine is +7. All right, probably doesn't seem too bad, just with a lot of rules. Hydrogen, kind of like its charge, normally 1. So all of these are +1. So the question is, what's the oxidation to the other element? Well, hydrogen, 4 times 1, +4, so that must mean carbon's -4. So notice in 2 different cases, this carbon was +4, this carbon's -4. So that's why I said it's not like the charges on the periodic table, because oxidation numbers just keep track of what happened with the electrons. Hydrogen, 3 times 1. So that means nitrogen has to be -3. Hydrogen 2 times 1 is +2. So oxygen has to be -2. And remember we said fluorine is always -1. Okay? But notice that where it said normally +1. Hydrogen sometimes can go -1 if you bond it to a metal. So notice all of these, they were bonded to a non-metal. Well, what if you actually have a metal instead? That means the hydrogen has to be negative. And why? Because as we said above, metals are always positive oxidation numbers, always. So hydrogen -1, so sodium has to be +1. Hydrogen -1, 1 times 2 is -2, so calcium has to be +2. Oxygen also has a normally -2, okay? So all of these -2, okay? So oxygen -2. Hydrogen has to be +2 to get me to 0, but I have 2 hydrogens. So you have to think of oxidation numbers for only one element, not all the hydrogens. So you got to kind of go reverse. Instead of multiplying, you divide. 2 divided by 2, so hydrogen has to be +1. Those are your answers, what you're boxing. Oxygen, 3 times 2, -6. That must mean aluminum has to be +6 to equal 0. but I have 2 aluminums. So that means each aluminum has to be the same number to equal +6. So it's got to be +3. 2 times 2, -4. So carbon's got to be +4. So what happens if you have like a transition or an element under the staircase? So determine the oxidation numbers for all the elements that you know first. Well, I know hydrogen's +1, oxygen's -2. So then leave the element in the middle to the end. So if that's 2 times 2 is -4, 1 plus something, -4 equals 0. So that must mean my arsenic has to be +3. But for oxygens, normally -2, what happens if you have a polyatomic called peroxide? So what happens with peroxide? How does it really break down? Well, when you do oxidation numbers, it's for one of them. So oxygen -1, oxygen -1. So if you add that together, -1 and -1 is -2. And I have 1 oxygen here and 1 oxygen here. And that's how it is peroxide. So O -2 and 2. So the oxidation number, if you have peroxide, which you see right here, hydrogen peroxide, that means the oxygen is -1. So I know hydrogens, 1, 2 times 1 is +2. That must mean this oxygen's -2, and -2 divide 2 is -1. So be very careful if you have peroxide or do you have just normally oxide. The name of the game is to make sure we get to 0. So let's do the following ones. Potassium's +1 because he's group 1. I don't know manganese. Oxygen's -2. 2 times 4 is -8. So +1 something -8 is 0. So that must mean manganese is +7. Sodium's always +1, group 1. Oxygen, -2. The reason why I didn't go after chlorine, because remember, chlorine, if it's with oxygen, can be positive or negative. So 1, -2, that must mean chlorine has to be +1. If you actually see a charge on paper, the sum of all the numbers equals the charge, not 0 now. So if you notice these two polyatomics, instead of equaling 0, I need to make sure they equal the charge that's on paper. Bromine could change. Oxygen, -2. 2 times 3, -6. And it's got to equal -1. And I know bromine's got to be a positive. So positive minus 6 equals -1. That must mean bromine has to be +5. But remember, those are your answers. Oxygen's -2. 2 times 7, -14, but it's got to equal -12. So -14 equals not -12, -2. So that must mean my chromium is +12. But here's the problem. I got 2 chromiums. All of the chromiums equal +12. I need oxidation for one of them. So 12 divided by 2, chromium must be +6. So let's do some example ones right here. You're going to test out your knowledge, okay? See what you can do. Let's do the first one together just to make sure we got this. Sodium +1. Don't know bismuth. Oxygen -2. 2 times 3, -6. So +1 something -6, and I don't see a charge on paper, so it has to equal 0. So that means that bismuth has to be +5. Okay? Oxygen, -2. 3 times 2, -6. It's got to equal 0. That must mean arsenic is +6, but I have 2 arsenic. So 3 divided by 2, so arsenic must be +3. So you're going to test out the rest of them, and then we'll check our answers in class. So how is oxidation number related to the last equation? Well, the last equation is called oxidation reduction reaction. So oxidation reduction reaction, you can abbreviate it redox. Everybody else does too. In order for you to have a redox, you have to have both oxidation and reduction. So the cool part is single replacement is always redox. And if you don't believe me, go back and look at right here. Chlorine by itself is 0. I see iodine with the charge. Well, that's iodine -1. I see chlorine with the charge. Okay, chlorine -1. Iodine seen by itself is 0. Okay, that's oxidation. So with oxidation reduction, every single is redox. But I can't say the other way. Not every redox is single. Okay, so with single replacement, they go hand in hand. But as I said, not every redox is single. When we do the examples, I'll show you this why, because you know there's examples coming. Now that you can determine oxidation numbers, probably did pretty good. How do you determine if something is oxidized or reduced? Because if the name of the equation is called oxidation reduction, how do you know if something's oxidized or reduced? The one that's oxidized loses the electrons. The one that's reduced gains electrons. So you got to remember basic chemistry. There's no electrons in the balanced equations, but basic chemistry involves transferring electrons. So the question is, where did the electrons go? Okay? So we got to get to the rules. Redox reactions. Redox involves the transferring of electrons from one substance to the other. And like I said, we're going to get very good at this because it comes back in chapter 20. Very, very important. All redox, somebody has to be reduced at the same time as somebody is oxidized. You have to have each one. It's not redox unless you have oxidation and reduction. So the species that loses the electrons is called oxidized. And what I mean by that is when you go from reactant to product, they had to have lost electrons. You're going to also see this happen. The oxidation number increases from reactant to product. So like say I have magnesium, and I say it went from magnesium +2. Magnesium neutral form 0. Magnesium +2, I see the charge. He lost 2 electrons. And how do we know that? Because from previous chemistry knowledge, that +2 cation, he lost electrons. But notice the oxidation number increased. I went from 0 to 2. That's how I know it's also oxidation. You have to, when you explain, you have to use either one. Either it lost electrons from reactant to product, or the oxidation number increased from reactant to product. Well, on the flip side, if it gains, it was reduced. And notice, with the example that I'm going to give you, is that the oxidation number decreases. So let's say I had chlorine, and I went to Cl -1. Chlorine is neutral. That -1 means that he gained electrons. And the -1, well, the oxidation number went down. When I say it goes up or go down, you kind of have to think of it like back in the day in math, like a number line. So +1, +2, or -1, -2. When the oxidation number increases, well, that's oxidized. And when the oxidation number decreases, that's reduced. However you want to think of it, just know which one is which. Explaining, they may want both. They may want you to talk about the oxidation number over if somebody lost or gained. But I have to teach you both because that's the AP way. So you have to realize who transferred to which element. And then you have to assign oxidation numbers to every reaction. So I got a little mnemonic device, a little trick. Leo the lion says grr. So Leo, loss of electrons is oxidation. And my lion doesn't say roar. Okay, my lion says grr. So gain of electrons means reduction. I have a teacher friend that also uses oil rig. Oxidation involves losing. Reduction involves gaining. Either one is fine. Cool mnemonic devices. So let me show you how this plays out before we do an example. Sodium neutral by itself is 0. Chlorine neutral by itself is 0. But then I have an ionic compound. So I have to use oxidation rules to determine the oxidation numbers. So sodium is group 1, so +1. Chlorine, -1 because it's got to equal 0. These coefficients have nothing to do with oxidation numbers. Coefficients balance equations. So coefficients balance equations has nothing to do with oxidation numbers. Okay? So you kind of have to use these brackets. If sodium went from 0, he was perfect, to +1. That means he went from 0 to +1. He lost electrons. And notice his oxidation number. His oxidation number went from 0 to +1. His oxidation number increased. Chlorine was perfect and went to -1. He gained electron. He was reduced. And his oxidation number went from 0 to -1. So 0 to -1, his oxidation number went down. So how do you tell AP in your explanation? So sodium was oxidized, chlorine was reduced. You list the reactants. So as you see right here, sodium and the Cl2. If by chance you forget to put the 2 on it, not a big deal. You could just say chlorine was reduced. So let's do a practice. Okay. I have iron neutral 0. Nickel I see +2. Iron I see +2. And nickel neutral by itself elemental form. Iron went from 0 to +2. Well, it looks like he lost electrons. So because he lost, that means he was oxidized. Nickel, he was already missing 2 electrons from the beginning, and then he became perfect. And what I mean by perfect, that means the protons and electrons equal each other again. So he was missing 2, and he gained the 2 that he was missing, so he gained. And that means he was reduced. So iron was oxidized, and nickel was reduced. Okay, like I said, you could put the Ni +2 on it, or you could just put the symbol. Calcium, elemental form 0. Hydrogen, I see that charge right there, so +1. Calcium +2, and neutral diatomic hydrogen 0. Hydrogen went from +1 to 0, so he was already missing an electron, and now he went perfect. So he gained, he was reduced, he gained that electron. Calcium was perfect. We did a reaction, and now he lost 2 electrons. So calcium was oxidized. So Ca was oxidized, and hydrogen was reduced. AP loves these type of questions where they want you to justify if the student's claim was correct. Okay? So, first of all, you need to explain or understand what justify means. Justify means you have to either prove the claim right or wrong. Okay? You have to use either math or explaining. Okay, so the word justify, you can use anything you want to prove the claim right or wrong. All right, so if he's saying that the below is redox, that means we have to use oxidation numbers, and that means you need to have somebody that was reduced and oxidized. All right, well, let's check it out. Iron and sulfur. Unfortunately, iron and sulfur don't have any oxidation numbers for me, as in rules, for me to learn. So I'm going to base their oxidation numbers off their charges. Sulfur is -2, so that means iron has to be +2. So when in doubt, if you don't have rules for an element, then you're going to kind of have to go old school. Look at their charges on the periodic table. Iron is a transition, so he could do anything he wants. Nitric acid, hydrogen, normally 1, oxygen -2, and I don't see a metal in there. 3 times 2 is -6, so that must mean 1 plus something equals -6, so nitrogen has to be +5. Iron, well, this 2 right there, that came from iron, so that iron is +2. Now, what about polyatomics? When you have polyatomics, you have to do polyatomics, do them separate. But with polyatomics, they have a charge. So that's nitrate. That's not nitrate. That's nitrate. So we have to determine nitrogen and oxygen based off equaling -1, not 0. So nitrogen doesn't have a rule. Oxygen, -2. 2 times 3 is -6, and it's got to equal -1. So nitrogen has to be +5. Well, those are your two answers. So nitrogen's +5, oxygen's -2. Hydrogen +1, 1 times 2, so that means sulfur has to be -2. So is the student's claim correct? Well, let's look at it. Iron +2, +2, nope, he didn't do anything. Sulfur didn't change, hydrogen didn't change, nitrogen didn't change, oxygen didn't change. Okay, so now justify. That's your evidence. Now tell them the answer. The student's claim is not correct, or you could say is wrong, due to no elements in the above reaction was oxidized or reduced. Simple enough. Get to the point. Okay? So your evidence, as you're showing AP right there, and then you actually have to answer the question. It's not valid because no elements lost or gained electrons. When you are actually explaining oxidized and reduced, please do not abbreviate it when it comes to essays. Stuff like this, that is totally fine. You can abbreviate it here when you're just listing who is oxidized and reduced. This is an actual AP question where they give you a sample example. And remember in the learning objectives, I want to say it's in 4.3 real quick. One of the learning objectives asks you, can you identify if something's acid-base, oxidation, reduction, or precipitate? Well, now let's practice it. Now that we've learned every type of reaction, let's do a sample AP question. So, if something is acid-base, all right, well, let's do a little reminder. Acid-base, you have an acid that reacts with a base. Acids start with hydrogen with either a nonmetal or polyatomic in the back. Bases, so acid, bases have a metal with hydroxide. And what are all acid-base reactions? Well, they're also double replacement. And they're also always going to form a salt and water. Okay? Well, justify. Well, we got to prove our answers. This right here, this is single replacement. So single replacement is never double. They can't be both, which means it's never double, which means can't be acid base. I don't even have an acid. Well, I do have an acid. I have a strong acid, but I don't have a base. So this one's not acid base. So I'm just making notes, not acid base. AgNO3, well, that's ionic, but I do have an acid. Okay, well, still not that one. Not acid base. Barium hydroxide, well, that's one of the 8 strong bases. Oh, look right there. There's a strong acid. So definitely acid base. And why? Because I produced a salt and water. Okay, so this reaction is acid base since both reactants are an acid and base. The products produced a salt and water. Okay? I labeled my evidence up here, but I still have to explain. Okay? So, definitely acid base. Well, before we get to redox, because redox has some work, precipitate. Did you form a solid? Well, this one, nope, no precipitate. I formed a gas. Part B right here, oh, look, there's my precipitate. Okay, so this is definitely a precipitate reaction. And why? So this reaction is precipitate since one of the products is a solid. There you go. Easy enough. So now the question is this redox? Well, if it's redox, we got to determine all oxidation numbers. Okay, so let me do this in a different color. So zinc by itself, elemental form is 0. Hydrogen's +1, chlorine -1. Zinc is always +2, chlorine -1, because 2 times -1 is 2. Diatomic hydrogen. So if this is redox, that means you have to have a substance, a species, a chemical that was oxidized and reduced. Okay? Zinc went from 0 to +2. All right, he was oxidized. Hydrogen went from 1 to 0. Okay, that guy already had one missing, so he gained, so he was reduced. And chlorine didn't do anything. That's okay. We just have to have at least one of each. So this is a reduction reaction since zinc lost electrons and was oxidized. Hydrogen let me first say, gained electrons and was reduced. And there you go. Always check if the other ones were reduced or oxidized, because remember, you can have redox on other types. So definitely redox. Okay? All right, so let's check this. Silver's don't know silver. Well, silver only has one charge, one oxidation +1. Oxygen -2, 2 times 3 -6. So nitrogen right there has to be +5. We already know HCl, +1 -1. We might as well do this one too, +1 -1. Silver, don't know. Chlorine -1, so silver has to be +1. So automatically, it's not looking too good. Hydrogen +1. Oxygen -2. 2 times 3 is -6. So nitrogen +5. Not redox. And what you tell them is since no oxidation numbers changed from reactant to product. Okay? Well, let's check this one down here. Barium hydroxide, well, we know this 2 came from barium. Hydroxide's a polyatomic. Anytime you see it in parentheses, do those polyatomics separate. But that's hydroxide, not OH. So if it has to equal -1, oxygen -2, hydrogen +1, so that's how it equals -1. So that oxygen is -2, hydrogen +1. We already know those. Cl -1, that 2 came from barium. And water will always be +1 -2. Well, as you check, nope, not redox. And why? Same answer, top and bottom. Okay? So I would like you to end this up. You try the same thing. I want you to show me why it's acid-base or why it's redox, why it's precipitate. But for redox, you have to check all 3 reactions because you never know. Somebody could be acid-base and redox, or somebody can be precipitate and redox. Okay? Long video, but it was a lot of information. See you on the next one.